everyone. In this video, we explain how we developed and evaluate a high-performance regressors using IES-CS dataset, and our objective was to minimize the mean absolute error on the dataset while ensure the model is properly fitted and generates well. Instead of only reporting the final MAE, we also focus on two questions. First, what do we do to improve the performance? Second, how we assess and improve the model fits. And to improve the performance, we first moved beyond a simple baseline model and adopted some other tree-based model like the random forest and attributes to also the like GBM to evaluate their performance. Also, in the pre-processing steps, we also do some feature engineering, and we are focusing on the combined structural climate and dynasty information rather than relying on the raw inputs. Also, we have moved the top 20%, top 2% extreme target value to reduce the influence of the outlier and apply a log transformations to stabilize the variance during the training. After pre-processing and feature engineering, we have compared the multiple regressors under in this way. Also, we have results that the linear regressions model is in the MA of 8.2422, 8.828, 8.8, and which suggests that the pure linear structure was insufficient. Also, in the random forest, we have the MAE of 8.3, and we use attributes in MAE of 8.2. Finally, we have the light regressors, and also the MAE is in the 8.24. So in this model, we found that attributes may be is the most fittest model, which it has the smallest MAE. However, we did not stop at a single model because boosting a method can behave differently across the data split. We construct a hybrid example combinations, which is in this way is a combinations of attribute boosts like GBM and the cat boost. Why we chosen this free model? Because the attribute boosts provide a stability and strong regulations, and also the like GBM captures more complex patterns efficiently, and cat boost can handle the category feature robustly. Also in this model, we have the use the fight for training with the early stop and regulations and combine the positions with the weight and averaging. This example achieved an average of the MAE of the 8.3 across the fold. Also, compared to the cost validations that we have used for the attributes, which is the 8.4, and we found that this combined model have better performance than the single on the dataset than the attribute single model. Now we turn to the second questions. How we assess and improve model fits? We first use standard trained validations and split it in compare validation against training behavior. Then we reduce a dependence on a single split. We also have to imply a 5-fold cost validations to evaluate the attribute boost models performance. After we convert prediction back to a original scale, that average score cost validation MAE was approximately the 8.6 8.4. In this confirmed that our model performance is not driven by one favorable patterns. Also, to further evaluate fit, we examine learning behavior and stability. We generate a learning curve using boosting model to observe how training and validation errors evolve as the training size increase. And the validation curve decrease and stabilize rather than diverging, indicating moderated but controlled overfitting. Also, from a bias variance perspective, the model did not exhibit a high bias since the validation errors were significantly lower than the linear baseline, and the generation gaps were made stable. So beyond the cost validation, we also test some robustness through the repeat random split. And we have compared this split in for the attribute boost and the combined model. And the attribute boost produced an average MAE of the MAE of 8.427 with standard deviations of the 0.1 sets. Also, the combined model have MAE of the 8.3487 around this way. Also, it has a standard deviations of the 0.1664. So, which state that our combined model is much more stable and it's very fit. Did repeat evaluations show that ensemble performance is slightly better on average and is less sensitive to a random sample variations. Also, we have examined the residential distributions predictions. And in this way, we compare to a single boosting model and also will enter and slightly smoother, stretching fewer extreme prediction error. This dialog step further support our final choice that choosing the combined model is much more better by compared to the residential distribution.